Welcome to the Internet of Things equation, a podcast when I talk about the Internet of Things domain both from the technical and business perspectives. I'm Łukasz Malinowski, the Internet of Things advisor and trainer. Space is the ultimate destination for the Internet of Things technology. Satellites are a perfect example of IoT devices operating in hard-to-reach places. In case of any issues, you cannot just send astronauts to the orbit to execute a manual reboot. My today's guest has over 30 years of experience in the space industry. He worked as an engineer, strategist, and subject matter expert. Hello, Jim. Thank you so much for taking the time to meet with me today.
Good morning.
You have an impressive experience in the Internet of Things domain and the space industry. Could you summarize your track record for the audience?
Yeah, so as you said, I've been in the space business for about 30 years, a little more. I started out my career at the French Space Agency in Toulouse, France. And then after that ended, I ended up spending 6 years in the former Soviet Union, working for the US government, helping stop brain drain of Russian scientists to North Korea and Iran. And did a lot of joint experiments with Russians on missile defense, unthinkable in today's world. Eventually ended up helping Elon Musk start SpaceX back in 2001, and left there in late 2002. Started a company called StratSpace, where I worked on a lot of space warfare, a lot of space communications, commercial systems. Ended up since about 2010 in the commercial space industry. I've been on 11 startups, either as a co-founder or in the founding team, and all the way from ISI, which is a radar company out of Finland, to York Space Systems, which was recently sold, to Phantom Space, where I'm at now, where we're trying to build both the launch vehicle and satellites and the constellations that could have an application with IoT.
Amazing track record. And I've got a question that I need to ask you. From that 30 plus years of experience, is the space industry getting easier or more complex from your perspective?
Yeah, both, I would say. It is getting easier because the capital requirements are coming down. When I first got into this business in the 1980s, space was the sole domain, really, of nation states because they're the ones who had the capital that could build these things. We then had some commercial industry, but now the commercial is the dominant player because private capital is able to finance a lot of these because the costs have come down. But this has really created a very complex environment to operate in, which is not a bad thing. But there are so many proliferating applications in space. It's a very bright future, but a very complicated one. I use the analogy that we're in the space industry really where Europe was in the late 1400s, sending galleons to the New World and coming back with gold, but nobody was smart enough to know what the New World would turn into 500 years later, and here we are. So space is the same. We're just in the very beginning. Anybody that tells you that there's no room for innovation left in space clearly doesn't know what they're talking about.
From my perspective, space is the ultimate destination for IoT devices, and satellite is simply an advanced IoT device on its own. Could you briefly characterize the hardware and software components for modern satellites for the audience?
IoT, really Internet of Things is what it stands for, is really at its most basic level is taking data from machines mostly, particularly at a low data rate, and taking that back to a end user or an operator that needs that data. Today, it's often done over terrestrial networks. And so the IoT in and of itself is not a space-based technology, but the terrestrial network is what supports it. And to your point about why space is the ultimate application for IoT, what we really want is our ability to monitor machinery, items, things that are very remote, that don't have easy human access to it, to be able to control them, to monitor them, and to do that globally. I live in Arizona in the United States, and you don't have to go very far from the city to find where you don't have connectivity. say with a car. Often they have connectivity, which is a form of IoT. With the proliferating space networks, we can achieve that globally. So you have the device you're monitoring, and then you have the end user. The space network is what comes in between. And so the thing that's changed the game is Starlink. And if you go back 30 years ago, 20 years ago, in the 1990s, there were a lot of people, Craig McCaw, for example, were talking about sending thousands of satellites up to have these networks. So this is not a new idea. What's new is somebody actually able to do it, because back then we were talking about hundreds of billions of dollars to do this, and now we're talking about hundreds of millions of dollars to do it. So it's a sea change, and Starlink, which costs more than a couple $100 million, has shown that the cost of networking, worldwide global networking in space, is far more cost effective than terrestrial networks in rural settings. In urban settings like cities, that's not true. But I think as the density of the satellites go up, it's going to be true. So my way of looking at this is, while terrestrial networks will always be there, the dominant force, I think, in the next 30 to 40 years will be all space-based networks, and that will clearly include IoT.
You mentioned that the number of satellites is growing, and I saw a diagram showing like the density of those things already on the orbit. This is extremely complex environment. So how can we manage that complexity and avoid crashing them onto each other?
It's a good question. I get it often. So first thing, space is a very big place, and it's probably more appropriate to think of it as sort of the equivalent of the Earth, in the sense that we have a lot of land mass. We have oceans where there's not much traffic, although there are a few shipping lanes where, I've been out on the Atlantic, and you will see lots of ships passing in certain shipping lanes. Same is true on land, where you have concentrations of vehicles on things we call freeways or highways, and then off the highway you may not see a vehicle for days or months. And so space is much the same. So there are very crowded places, the equivalent of highways in space, that are popular for a number of reasons related to the physical characteristics of those orbits. What's going to happen over time are really three things. One, we have to go away from putting everything into the same orbit, and that's partially the fault of rideshare, and that's where a lot of these satellites, say 100 of them, go on a SpaceX transporter mission and go to those same orbits, because that's the popular orbit to go to. That creates debris. One man's satellite is another man's debris. And so the other thing we have to do is to be able to launch frequently enough so that we can put these satellites in different orbits so that they don't collide, but that they also allow the Earth's atmosphere to bring it back. What people often don't understand is that even at, say, 450 kilometers, there's still enough atmosphere up there, and these satellites are going 25,000 miles an hour, or about 7,800 meters per second. There's enough friction there that it brings the satellite down within 3, 5, 10, 20 years. So that's a natural cleansing of the orbits. So you want to be able to design your satellites to be replaced, much like an iPhone or any other Samsung phone gets replaced every few years for technology upgrades, and that requires really innovation in space transportation systems, which is what I'm focused on, to be able to have a wide spectrum of types of transport, all the way from the large Starship to the Falcon 9 to the smaller Daytonas like we're building. And that will then allow satellite operators to go to places that aren't as crowded and aren't as dangerous. And then the third thing I think is helpful, and I'm not one to press for government regulation, but I do think if satellite operators are required by governments that license them to have third party collision insurance, that sort of capitalistic effect is the insurance companies are going to price in the risk of what orbit you go to. So naturally, people are not going to go to these orbits unless there's a big payoff. So absent that sort of that financial incentive, we've got a mess coming. And of course, the U.S. Air Force has a very good system to track everything that's in orbit. and they share that data now. It's called the JSPOC, and that was as a result of some of the work I did at Iridium, where we lost a satellite to a old Soviet booster from the '60s that was still up there, and here we are 40 years later, and boom, we lost a satellite. So the Air Force, is trying, and so that's really kind of a fourth thing, is a lot better monitoring. There's a number of companies, Leo Labs, one of them, that sells these data for where objects are, and you can do your own analysis to see when you're in danger.
This is the common theme I see across the IoT landscape, that technology is ahead of legislation. And as you said, once legislation will catch up and we've got that money intensive as well, then things will be a bit better organized. Let's go back to the satellites themselves. You mentioned that satellite is designed to operate for roughly 10 years in the orbit, and 10 years is pretty long lifetime. We can remotely upgrade firmware to manage that device, but there is not a good way to remotely upgrade hardware components. So, how do you manage the lifespan of a satellite in the first place?
Well, right now, the main limiter of lifespan on satellites is power, and the solar panels, which generate the power just like they do on Earth, they suffer from degradation due to radiation. So there's the Earth's atmosphere, and particularly the magnetosphere around the Earth, protect us from this damaging radiation. If we didn't have it, we would probably all suffer a lot more cancer and things like that because of it. So, in that sense, it damages the solar panels and they degrade over time. And eventually, satellites don't have enough power to operate. And that is one of the main reasons that satellites die. The other one is if they need fuel for maneuvering, they will run out of fuel. You're right that the hardware is not easily upgraded. The software is, and there's a movement, and I was one of the intellectual fathers of this, towards software-defined satellites, which, much like your iPhone or your Samsung, you get a software upgrade, and it's really kind of a new phone. I'm old enough to remember when we had Motorola cell phones that were hardwired, and we called them bricks, and that was in the '80s and '90s, and those couldn't be reprogrammed. You could probably flash new code into it, but largely the phone was what it was because it was mostly hardware. And phones now are all software defined. So I think satellites will go to that. It's important to understand that satellites are typically 10 to 20 years behind the technology curve of consumer electronics for a number of reasons, mainly due to, the risk of implementing new technology in space is high, and nobody wants to risk their money on new technology for the marginal gain. But as time goes on, this is what you'll see.
You mentioned that satellites are behind. Could you give us some insights about how do you design the electronics inside the satellites, and how much does it differ from electronic design process that we've got for devices that are running on Earth?
It's a good question. So, in the old days, in my early years in the space business, we used what we called radiation hardened electronics. So, the integrated circuits and the other devices in the electronics parts category were susceptible to radiation damage. So there's just general radiation that happens, much like if you're near a nuclear power plant that's spewed the radiation. Plus, there's something we call high energy particles that's really unique to space, and the high energy particles will go right through the device, and it doesn't create a hole per se, but it does displace some molecules of silicon in the chips, and that can cause damage, right? And they call this latch up. So the device can latch up and not work anymore. Astronauts, and I find this spooky, report that when they go to sleep on the space station, they can see what looks like asteroids or shooting stars in their eyes, and these are high energy particles that are causing their eyes to react to these high energy particles. So you have in the old days we had to design around that by making our parts hard. As the feature size of electronics has gotten smaller, for a while their susceptibility to radiation got worse, and at one point, about 10 years ago, as the feature size and the chips got smaller and smaller, it actually got more resistant to radiation, much to my surprise personally. But there's a lot of physical responses to that. So today, we mostly use commercial electronics in our satellites. It's available that all the rad hard part lines have gone away. There's a few of them still alive, mainly for military applications. But commercial electronics actually work very well in space. And what you do is you create either voting architectures so that if you have an upset on one device that it can outvote that device if it's not working properly, or you have redundancy in the electronics in case you get one that's totally gone. It really depends on how long you want the spacecraft to be up there. So Iridium first generation, we designed it for 5 years. They lasted 17, 18 years, and they were just pretty much commercial electronics. So they can be pretty good. They'll outlast the solar panels a lot of times, the solar cells. There's not much we can do about that with the technology we have today. They just die over time.
You mentioned the concept of software-defined satellite that you created. What is the concept about? Because you briefly touched about it, but let's go into the details. And is it connected to the digital twin, so that virtual representation of a physical device, or it's based on some different aspects?
Yeah, so it's not much different than your computer that you use, whether it's a Mac or a PC. Same thing. I mean, what really you're interacting with on your computer, you have a physical keyboard, and you have a mouse and a screen that you can get the photons into your eyes, and speakers that you get the sound into your ears. But what you're really interacting with is software, and you can take a computer like my Mac, for example. I can run Windows on it, or I can run the Mac OS software, and that's a software defined computer in that absolute sense. So if you think about satellites, really kind of going back to the phone analogy, the old phones had buttons. You couldn't change the buttons because they're physically what they are. Whereas now my iPhone has software buttons, and I have to find the place on the screen. There's a touch screen. So it's really exactly that same concept where, as long as we have a processor and we have power and we have a communication system, we can cause the spacecraft to do different things. So what this allows you to do is to have different spacecraft, for example, layered in memory. So you might have one spacecraft that's an IoT data transfer system, and then another spacecraft that's a more broadband data transfer system, and then another part of it, another software part of it, would be a data backhaul for other satellites. So you could have all three of these functionalities simultaneously running in the satellite. And based on the data that comes in, you can route it to the different parts of these satellites, which, like, you can have multiple screens up on your computer or all running rather separately. So I can run a CAD system, a browser, and my email all at the same time. So that's where satellites will go. We're designing our Phantom Cloud system to be exactly that, where we have these multiple satellite personalities, if you want to call it that, that'll operate simultaneously on the operating system. So you still have to deal with the hardware side of it, because you still have to move the bits in and out, and that takes either lasers or RF systems, and you still have to be able to point the satellite to get the right amount of power. And with antennas, we're becoming more and more electronic with phased arrays, so that can all be electronically pointed. So that physical constraint is going away. So it won't be as independent as a phone is, but they'll work towards that.
Your analogy to electronics like computers is very good, and that actually brings me to my next question, because recently I read an article about cyber attacks targeting satellites. Could you share your takes on that? How can we defend satellites against those attacks, especially satellites that are already in the orbit, that are not yet designed, but are in the orbit, and we need somehow to defend those systems?
Yeah, this is a good question too. It's what we in the U.S. call a 900-pound elephant in the living room. It's something that people seemingly don't talk about, but it's a big presence that a lot of us know is there. It's not really been exploited. There was an incident with Starlink that happened about a year and a half ago, where a nation state took control of one of their satellites through a hacking process. So this kind of issue has long been of concern to the Defense Department of the United States, and they took care of it with encryption. In the old systems, only ground stations would talk directly to the satellite as it's overhead. So if you encrypt that link, unless you can break that encryption, you can't get in and issue commands to the satellites and get in and get a hold of the data. But once they're networked, which I think is the future, now we've got exactly the same problem that we have on the internet. And so where there's a motivation, the hackers are going to definitely come together there. And the U.S. Air Force, in particular, and I was involved with some of these activities, has started crowdsourcing how hackers will access satellites by putting satellites up and asking white hat hackers to try and get into them. Once quantum computing becomes operational, we really have a problem because now we can break encryption. And so I think there's, if an entrepreneur is out there and wants to make the next $1 trillion, solve this problem, because it's something I don't know how to solve. It's something most of the people in the business I'm with don't know how to solve. So there has to be this merging of domains that we see on Earth into the space industry. We've been long too isolated, to stovepiped, as we call it. In our own space world, we have to borrow from the people that understand how we secure terrestrial networks and so forth. It's a different problem, to be sure, but it's the same basic problem, and probably the stakes are much higher because a lot of this involves nation state national security. It involves more and more commercial value, commercial assets that can be hijacked, stolen, changed, altered, and so forth.
I think that the quantum computing will actually mess up the security as we know it, because all of that is built on that asymmetric type of encryption. Once we've got quantum computers
Yeah.
operating, as you said, they will be able to guess those random numbers that actually are the key of the asymmetric encryption, and then everything is clear text for them. So not only the space industry will be impacted, but also financial systems and everything that we are using, right? So the single principle is keeping all of our data secure currently, which is a huge issue in my opinion. And I totally agree with you. We know that that challenge is ahead of us, but we do not really have a good idea how to solve it as for now. You mentioned that we've got white hackers trying to access satellites. There is interesting attack vector where we've got the satellite to satellite communication. As you said, it's more like the internet, so it's not one to one. We will get to that mesh system of satellites, and now we've got the challenge that we need to defend the whole mesh of satellites, because someone can basically upload a virus and make that virus spread across the whole fleet of satellites. I believe that we are starting to tackle that issue, but probably we are not there yet in terms of how to solve that, unfortunately. You created the concept of space situation awareness sensors. Could you elaborate on what are those sensors and how you create this space situation awareness?
So I'm not certainly not the intellectual father of the idea of space situational awareness or sensors to do that, but I was involved in developing a number of them. We would look at things like star trackers, which look at a field of stars and tell you which direction you're pointing by recognizing the pattern of stars. And then you can do things like subtract things out of that don't belong there, and deduce that something must be there. And through some pretty sophisticated mathematics, you can determine where it was and what orbit it might be in, and through correlation with other databases, find things that might not otherwise be seen. If something's close to you, you subtract out the negative image of what stars are missing, that something's blocking you. These are sort of tricky ways to do it. There are a lot more, I would say, meat and potatoes, we call it, kinds of sensors, which are just simple telescopes that are looking at everything in the sky. They're measuring, what they can of them. There are ground sensors that do this. A lot of stuff gets kind of sensitive, so I'm going to be vague. This is something of great interest. Radars. There's a lot of radars. I mentioned that early to talk about space traffic. So there's really kind of two levels of interest. So what's up there and where is it? And then in each one of those things, what does it look like and what does it do? And really, those are the two questions that nation states mostly are answering. I think the first question, it has a commercial application to avoid running into other satellites, as we discussed. The second one, potentially adversaries could disrupt commercial operations with space mines and things like that. This is not a secret. This is out there discussed. And more and more as commercial space becomes successful and governments begin to rely on commercial space, they will become a target for adversarial action from other nation states.
You founded the Phantom Space to remove entry barriers for space applications by increasing scalability and cost effectiveness of getting things into the space. So that's a huge undertaking. Could you give some details on how you implemented that breakthrough?
Yeah, we at Phantom Space want to make space more accessible and much more rapid in the access. And by that, we like to say we want to be the Henry Ford of space, who did the same thing for terrestrial transportation through mass manufacturing. So that's the same playbook, as we say, that we're using here. We see the future of space really being one where some companies have launch vehicles and some companies don't. The dominant ones will have launch vehicles and do things with them other than launching other people's satellites. There's a strategic power in having your own launch and being able to launch your own satellites, make them and launch them. Witness Starlink, that the only way that worked was SpaceX had their own launch vehicle that they launched their own satellites, and now they're the only ones that could put 5,000 satellites up. A, because they control the pace at which launch is and the priority of launch. B, they can capitalize this at about half the cost of everybody else because they're doing it on internal costs. And then three, they can choose who competitively might launch on their vehicles or not. And there's nothing that says you have to launch everybody's vehicle. So in that sense, we're taking the same page out of that playbook and applying it to Phantom Space. We think that while SpaceX has done a marvelous job and really changed the launch industry, we know and we understand, Chris Thompson's with me. He was one of the early guys at SpaceX along with me, and he stayed a lot longer than I did. We understand that SpaceX is all about Mars and it's about human settlement. All you have to do is look at what their mission statement is, which is to make humanity and all life multiplanetary. So they're going to continue to focus on that. We're thinking of this in a commercial aspect of, how do we enable the commercial space industry to grow and proliferate? And we believe that we're still in the phase of the industry of needing to have infrastructure. Launch is part of that infrastructure. There's a curiously high demand for satellite buses, so we're building those, and we have a number of customers already. And then we also believe data backhaul is a big choke point for this industry. So that's the origin of Phantom Cloud. And that data choke point can ultimately be, satellites. We'll start there. It could be IoT. It could be any other data that needs to be moved globally. We don't necessarily see ourselves as focused on one element of that. Overall, we want to build the backbone that other people can put their applications on top of.
What are the major cost factors of getting things into the space nowadays, and how can we reduce them?
The number one factor in getting the cost down is the rate of launches you do a year. So you have, a number of people, we call it a standing army, that costs a certain amount per person. And the more you have, the larger the cost. But the more launches you have, the more you can amortize those costs over a greater number of launches, thereby reducing that contribution to that launch vehicle cost on a per launch basis. The second thing that happens is when you launch a lot, if you build them like we're planning on doing, then you get a cost reduction based on a learning curve. So an automobile, for example, you may drive a $40,000 automobile, but I guarantee you the very first unit, if you look at what it cost that company to build it, it was $100 million. And so they've reduced through millions of them being manufactured the cost from 100 million to $30,000. So we're going to do the same thing with our launch vehicles and our satellites by building a lot of the same ones. We get that cost reduction. And because we're smaller, we'll build more to launch the equivalent amount of mass to space. And then the third thing is reusability, which is proven by SpaceX, and this reduces your replacement costs. And this is more and more important the bigger you get in a launch vehicle. When you're the size of Starship, it's extraordinarily important that they be able to launch them and launch them 10, 20, 30 times more per vehicle. So we plan to do the same thing. And so that's how you get the cost down. You also have to work the launch range side of it. So the launch sites are limited. You don't find the launch sites anywhere because they're noisy, they're dangerous, it annoys the neighbors and so on, except in Florida. They seem to love it. But we've set out to very early to corner that market, if you will. We see it as sort of a real estate play to have as many launch sites worldwide as we possibly can to get that rate up, because that'll be ultimately, I think, the throttling of the industry is how many of these launch ranges are available, and the throughput there will sort of put a throttle on a downward spiral in price.
And those launch places, they need to be located in very specific areas of the globe, right? So it's not like you can launch from any place. As you said, it's very strategic move to actually acquisition those launch places ahead of time, and then build up on top of that the capability that you created.
The regulatory authorities generally don't want you to drop your boosters on land. That being said, the Chinese and the Russians do it, and they kill people with it. And there's toxic fuels that are remaining in their boosters that they'll land in Kazakhstan, in case of the Russians, and in China they'll land. And I've seen videos on Twitter or X, I guess they call it now, where these Chinese are running out to recover the metals and so forth off these spent boosters, and the peasants and the people who are doing the recovery they're dying from poisoning from the fuels. So that's a bad idea. I mean, just generally a bad idea. So you can physically launch from anywhere you want. You could launch something from the Kremlin parking lot if you like. But in the West at least, we generally launch out over water because there's no people. There are very few people, so the probability of somebody getting hurt is minimal. For my lifetime, that's not going to change. What may change eventually is where we can launch from inland areas, much like airplanes. Because if you look at airplanes, they carry, compared to, say, my rockets at Phantom, they carry more fuel than we do, and they'll fly out over millions of people out of a big city. Nobody thinks twice about that. And they're noisy and all these things. There is a future where those happen. That's on our long-term path. Technological evolution is to be able to launch horizontally out of airports in the middle part of the United States, for example. And that will ultimately, help bring down the costs. But that's probably a generation away, I think, probably 10 to 20 years.
Quantum Space offers launch services, spacecraft design and construction, and constellation launch and deployment. And that basically feels like satellite as a service model. You are creating that backbone for others to leverage and to put their things into the space. From the operational perspective, that is a huge undertaking to manage that complexity. Could you give us some hints how you manage it, how to keep all the things operational? Because we are speaking about advanced technology, number of things that can and probably goes wrong on daily basis. So how you handle that?
Well, first of all, let me say, while launch is very hard, and it's very intolerant of failure, it's not a new technology per se. It's something that has been around for 50, 60, 70 years, and it's successfully been demonstrated many times over. You're not really dealing with something fundamentally new here, like quantum computing. You're dealing with an existing technology, and and it's mastering the operation of it, it's mastering the engineering of it, it's mastering the implementation of it. Same is true, even more so with satellites, which is less, I think, difficult than the launch vehicles from a technological point of view or from an engineering and management point of view. Satellites, last year we launched 3,000 plus satellites. At the time I got into the business, we never even launched three satellites in all of our history, and so it's proliferating in massive ways. And so there's, just like computers. When I was in college, I had to build my own computer because I couldn't afford a Dell computer, for example. Now you wouldn't even think about, because you can go buy a computer for $200 off of Amazon and be done. And so that kind of proliferation is happening already in the satellites. I don't think that's going to happen with launch vehicles. But you're left to focus on, once you have a demonstrated launch vehicle, you'll have to focus on operations. So we think of Phantom more as sort of the equivalent of an airline, like Southwest Airlines, like Delta, like American, that we have to focus on the operations, getting stuff into orbit, but yet we still have to build our own plane. So there's no Boeing out there that's going to sell us or Airbus that's going to sell us a rocket, and we have to go buy that. So that's the early stage of this business. It speaks to sort of the relative complexity of that. If you break it up amongst its smaller elements, it doesn't seem as daunting. And fortunately, we've been able to convince investors over the years that, like we say, we can walk and chew gum at the same time, but that we can manage this kind of complexity. And that's where the real value in Phantom will come from, is being able to put this whole operational scenario together.
So you create the framework. Once you've got all those procedures in place, then managing the complexity is getting easier because of all of the experience that you gather along the way. And as you said, maybe you will create the Airbus equivalent. So you will create the planes yourself. And once you've got the hardware in place and software, of course, to operate that, then it will get way easier to launch things into the space. And as a result, the cost will go down, and we will see the huge explosion of the potential of getting things there. You were the first vice president of business development at SpaceX. What would you advise to someone thinking about starting the space-related business nowadays? What are the main factors to include? And is it even worth it? Because you said that there is still tons of potential for innovation in space, so probably that's worth it. I'm pretty sure that is also extremely tricky to start with. So, what are your best advices for someone entering this field?
Well, I mean, it's sort of general advice in life. Make sure you're passionate about what you're doing. If you're doing it for the money, that you're not going to succeed. If you do it because you love it and you're passionate about making something happen and you're good at it, and it's something that there's a demand for, that people want to buy, you'll be successful, right? In space, the challenges are, you can't do it by yourself. It's not like a software company. It's not something that you can just put a couple people together in a room and get it done. This takes large numbers of people. Generally, it takes a lot larger amount of capital, so you have to be good at raising money. So if you're young, I would say start with something less ambitious, make it work, get it sold, and move on to something more ambitious. The other thing is when somebody approaches you, don't always say no. One of the guys that works here, his grandfather was telling me a story last night about how he was in business with Ray Kroc. And if you don't know who Ray Kroc was, you probably heard of his business, which was called McDonald's. And Ray Kroc, before he was at McDonald's, was involved in some agricultural business, which my friend's grandfather was with him. They sold it. Ray Kroc went into selling these milkshake machines, and he discovered these two stores owned by the McDonald's brothers out in California, and that ultimately became the McDonald's enterprise. So he approached my friend's grandfather and asked him, "Hey, would you like to be involved in this business? I got these two hamburger stands out here in California." And the guy said, "Nah, I'm going to stick with my agriculture." So, sort of the same thing with Elon. When he called me out of the blue, he seemed kind of crazy, and his idea was crazy. But look where it got, right? It's an amazing thing. You just don't know. So when you don't have to do it yourself. And I would, frankly, I would start was working for somebody else in a startup if this kind of thing interests you, and learn what you can learn, because there's, young founders, they do succeed, but they're rarer, particularly in the space business. I think the older founders have a big advantage in that, we don't have the energy of the young guys, but we don't really need the technology supremacy. We need sort of the experience to know where not to step on a landmine, if you will. From a financial point of view, that's the most expensive thing in the space business, is making mistakes. So that's why the space industry really does favor older founders in that sense.
Speaking about sharing experience, how can our audience follow you to learn from you and to be up to date with your impact on the space industry?
First of all, I wrote a book about all of the history of new space, called Breaking All the Rules. It goes into a little bit of my story and how, I was there for a lot of this. You can get it on Amazon, Breaking All the Rules. And then the second thing is, you can follow me on Twitter, James N. Cantrell. You can follow me on LinkedIn. I'm not a prolific poster, but I definitely post.
Thank you so much for finding time to
Pleasure.
speak with me today, sharing your knowledge and your experience. There's a tons of value in what you shared.
Thanks for having me.
Thank you for listening. Go to thefingers.com to find more materials about the Internet of Things domain. My name is Łukasz Malinowski, the Internet of Things advisor and trainer.